Welcome to this week's installment of our weekly reading group. Today, really excited to welcome Felipe Polo. He's going to be presenting his paper, Efficient Multi-Prompt Evaluation of LLMs. He's from the University of Michigan, and the research introduces PromptEval, which is the new method for estimating performance across a large set of prompts, drawing strengths across prompts and examples to produce accurate estimates under practical evaluation budgets. So yeah, really excited to go through this today, and welcome to the session. The floor is yours, Felipe.
Oh, thanks very much, Daniel, for the introduction, and I'm very happy to be here presenting to you guys. So thanks very much for the invitation. I think this is a great opportunity to share our work. So first, we're going to start with our problem, and then we're going to present our solution. Then we're going to have a quick demo so you can see how our solution works in a practical situation. Then we go to some experimental results for some benchmarks. And then finally, I'm going to present to you like one extra application of our method, which is of best prompt identification. This is the problem we're like trying to solve. So the thing is that LLMs are very sensitive to the prompt you give to them. So if you give two different prompts that mean the same thing, the LLMs are likely to produce different results. And sometimes their results are very different in the sense that they are gonna be, one can be a very good response and the other can be a very bad response. So here is like a picture I took from another paper. And here they are basically measuring like what's the accuracy of an LLM in a certain task for different variations of the same prompt. So basically you can see that here, like the content of the prompt is the same, but they just write in a different way. So like they put some extra spaces, or they put like words in upper or lower case. They use different separators and etc. And like for different variations of the same prompt, they can have like a very high amplitude of accuracies. So you can see that in this task, for example, in this, they show that maybe this is the most extreme example they have in their paper, but like they have a gap between the best prompt performance and the worst prompt performance, like 80%, which is like very, very high, right? So this is like a problem that we don't know exactly how to solve, but and like if you want to evaluate LLMs and compare LLMs, this is a very important task, very important problem, because the performance of your LLM depends on the prompt you give to them. So they file like, let's say, a final rank of LLMs you have, like for your leaderboard, also depends on the prompt you give to them. So this is one of the instances of this problem. There's another paper that shows the same problem. Here, like they have more like rephrasing, paraphrases of the same prompt. So you can see some examples in the left, but they are all semantically like equivalent. And on the right side, we have the distributions of performances across prompts. So you can see that this is like, we can see like this phenomena in different cases, different benchmarks, different papers are presenting the same results. So we can see that this is a problem that is like basically replicated by different authors. And that's the problem we want to tackle. Finally, we have some example from for MMLU. And this is from our paper. So we also do this study. So basically what we do here, we have 15 like state-of-the-art LLMs. And we have these 57 subjects from MMLU. And we basically, each one of these LLMs are going to respond to MMLU using 100 variations of the same prompt. And here you can see like what's the distribution of the maximum accuracy or maximum performance in MMLU minus the minimum performance across like this 57 subjects. And you can basically see that like for some LLMs, and of course some are less we have a less variable performance distribution, but some of them like we can have a very high difference of maximum and minimum performance depending on the prompt you give, which is like also give us more evidence that this is a very, very important problem. And like, for example, MMIU is a very, very important benchmark. And many people use this benchmark to compare models, but like people usually use a fixed prompt choice for this leaderboard. But like, what if I change the prompt format? What happens, right? Maybe the ordering of the models are not the same. So what can we do? So basically, this is basically this slide. So if models are sensitive to prompts, how can we like order them? Right? Maybe this ordering is not reliable, or it's very sensitive to the prompt we choose. Okay, I have some lag now. Okay. So one proposed solution to this problem is basically, let's say that we have like a pool or like a population of prompts, like variations of prompts, and these are all like reasonable prompts, right? And what we can do is basically let my LLM solve this task across all possible prompts in my pool of prompts. And then we can basically get some summary statistics for this specific LLM. And then I can use the summary statistics to compare models. So for example, let's say I have 100 prompts, and then I make my model respond to MMIU using these all 100 prompts. And then I can just maybe get the median performance of this LLM or average performance of this LLM. And then I can use this unique number to compare LLMs. This would be more robust than just like choosing one specific prompt and using that number to compare LLMs. But the problem with this approach is that the cost can be very, very prohibitive, right? Because here, for example, like if we just have 200 examples, like what I mean by examples here, I mean different questions. Let's say I have 200 questions, and which is like very, very small. And let's say that I have 200 ways of rephrasing the same prompt. So in total, in this case, we would have 40K evaluations, which is like very, very high. So how do we make this cheaper? So that's our main goal in this paper. So we want to propose a method that people can use to produce like reliable performance distribution estimates across prompts in an efficient way. So before we produce, I show you our solution. I wanted to talk about a bit of notation that we're going to use and like what's our concrete objective here. So let's say that you want to we want to get an estimate for the performance distribution of an LLM in a certain task. And by this performance distribution, I mean across different prompt formats or different prompt templates. Here, we represent our set of examples or questions as the set curly J, which is a set of size J, capital J. And then we also have a set of prompt templates that we represent as curly I, which has size capital I. Here, for each one of the combinations of prompt, template, and question, we have something that we call correctness. It's just represented by Yij. And this is a number just 0 or 1. It's just basically if this specific prompt template got the question J correct or not. So if it gets correct, this Yij is 1, otherwise it's 0. So basically our main objective here, like in concrete math terms, is to estimate this distribution of prompt formats. So it's here in the bottom. So this distribution is just represented by capital F. And this is just an empirical distribution of performances. And these performances are represented by Si. And Si is just the average of the correctness for a certain prompt template I. So basically, we just want to compute this distribution of performance across different prompt templates in an efficient way. Like, let's say using less than 5% of total possible evaluations. Okay, to do that, we use a model, and this is our model. So basically, here we are trying to model the probability of a prompt I getting a question J correct, and giving like a set of parameters, and these parameters we just call psi and gamma. And as you can see, this is basically a logistic model. So as we are used to doing machine learning. And we have two components in this logistic model, which is just f psi of xi and g of z j. And basically xi is just like a set of covariates that we have to represent each one of the prompt templates. And zj is a set of covariates that we use to model also each one of the examples or questions. And this f of x is basically just a measure of how good the prompt I is for this specific LLM we want to evaluate. And the g of z is just like a measure of how hard this specific question is for this LLM. And basically, we have this model, and these parameters, psi and gamma, we need to learn them. So we can learn them, for example, using stochastic gradient descent, backpropagation, as we are used to do. So this is basically like in the end of the day, this is a neural network that we want to learn. And like as an example of the X size, this can be, for example, some embedding for the prompt I, and Z is just like an embedding, for example. And these parameters are learned minimizing some loss function, or we can see like this as maximizing the likelihood. Okay, so finally, like let's say you estimated these parameters psi and gamma. Then we need to estimate the performances of each one of the prompt templates, right? So we do that by using this formula here. So let's say that you have conducted a certain number of evaluations, and these evaluations are encoded by this set of pairs that we call E here. Here is just like the set of IJs that we see basically evaluate. So you can basically see this problem as you have like a matrix. So in the rows of this matrix, you have different prompt templates, and in the columns of this matrix, you have different questions. And basically, you observe some entries of this matrix. So in the end of the day, you're kind of doing like some kind of matrix completion here. So basically, we see these entries of this matrix, and these entries of this matrix are going to be represented by this E, set E. And then we observe this E, we fit our model, and then we use this formula here to basically estimate the full performance of the model. Basically estimate the means of the rows of this matrix, which is give us like the performance of each one of the prompt templates. And this formula here is just an estimate for the conditional expectation of the performance of each one of the prompt templates, which is just like a combination of two parts. The first part is just a part that depends on the data that we see. So basically, I'm just averaging the Y's that we observe. And a second part that depends on the model that we use, that basically we are just averaging like the predicted performance on the unseen entries basically of this matrix. So after we get this estimate, which is just an estimate for a conditional expectation, we can just plug these numbers in the empirical distribution, and we get like a predicted performance distribution for different prompt templates, which is given in the bottom of the page here.
Good question. Sorry, on the previous slide. Sorry, yeah. I got it for a second, but sorry. So the function F and G. How are these functions parameterized? Sorry, did you say they are neural networks? Did you say?
Oh, so I think there are different possibilities here. I think you can just imagine this F and G to be like multi-layer perceptrons. So
okay.
that's it.
So obviously they can be whatever, obviously, but and just like how hard good prompt I is like, but by goodness of the prompt, this is just like how, just like how this template enables the LLM to be more likely to get the answer correct, basically. So like how it's kind of like how does the performance of the model depend on the prompt, basically, and good means that it's more likely to get a good answer from the LLM, basically, and hardness is like okay, yeah, I got it. So the example is like the task. So like let's say in this example we had 200 different questions. Like so J here is like the actual example itself, and I is like the instantiation and the rephrasing of that example. Is that what the difference between example and prompt is there?
Exactly. So like the I's would be the question itself. So let's say, oh, what's the square root of 4, for example?
Yeah.
Then the I would be like maybe some prefix that comes before the question. So it's like, oh, please respond to this following question, or please respond to this following math question. Like these are possible variations.
Okay, got it. But also the examples you gave at the very beginning of the talk was like sometimes it was more than just prepending or appending instructions. It was like which of these two things is best, or out of this thing and this thing, which is I think it was on the next slide maybe here. Like these examples you gave, like were a little bit more than just like prepending and appending. It was like rephrasing.
Exactly. Yeah.
So is this included in the kind of the different examples for any given? No, I'm using the wrong word. So is this included in your like reprompting of the same example? Motivations like this?
Yes. So
okay.
I think that there are different ways of you creating these different variations, right? One of them is like using different formats that is basically in this slide that I'm right now. So basically change how your prompt look like, basically. But and this is like maybe like you wouldn't expect this to make any difference, right? But it makes a lot of difference sometimes. You can also like do paraphrasing, which is like this example here. So you can basically write the same question in different ways. So this is one possible. And there's also this other possibility that I gave the example, is just basically just appending like different texts on the top of the question.
Also, is this graph on the right corresponding to this template on the left, or are they different?
They are different, but they are from the same paper. They use data from the same paper, but they are different.
Okay, got it. I was going to say I'd be quite surprised if the spread for some of these models was that big for that exact reframing. But anyway, that makes sense.
This is not exactly for this rephrasing, but even for this rephrasing, we see lots of variations.
Okay. No, interesting. Okay, awesome. I think that's everything. So I understand the mathematical model. I guess going back to just the slide with the equation again. So that makes sense. And then on the next one, I think that made sense as well. Obviously I'd be really interested to learn, well, I guess you're getting to this, how you train these two kind of multi-level perceptrons and everything, but I guess we'll get there.
In the paper itself, like we actually use just a linear layer on the top of a pre-trained embedding, and this shows to be like good enough. So we don't even train like a deep neural network for this.
So just one linear projection on top of an embedding model, basically.
So in the end of the day, this is just like a logistical regression.
Okay, got it.
But of course, this can be more complicated if needed.
Yeah. Okay, makes sense. Cool. Okay, thanks.
Of course, do you have more questions, or?
I don't think so. I just And well, I guess, sorry. So like this final thing that you're getting, you're estimating the performance. And what is it actually? Just I'm trying to understand what you're basically trying to learn an estimate to the probability distribution of, like, unless I'm mistaken here, but like of how good a model is. So maybe I've got it totally wrong. So obviously, just correct me if I'm wrong. But like,
Mhm.
obviously, what you could do, you have a model, you have a standard prompt, let's say, and then you could have like 200 variations of that prompt,
Yeah.
and you would get this like, well, maybe it'd be Gaussian, maybe it would not be Gaussian. It might be this like arbitrary probability distribution across that prompt and all of its variations for a given model.
Mhm.
And what you're trying to do is estimate that like probability distribution using a smaller number of samples. Is this kind of broad what you're trying to do, and you want to predict like how, like, almost like what the variance would be, what the variance in performance would be, given a prompt, and like when you then change that prompt, how that's going to impact the performance of the model without needing to do like tons and tons of queries? Is this kind of the distribution that you're trying to learn in an efficient way?
Yeah, so I think you're correct. So like I think one way of seeing this is like the data. If you had the full data, the data would be a matrix, right? So in the rows
Yeah,
you have different like variations of prompts,
yeah,
and in
yeah,
columns you do have like different examples. So in the end
yeah,
of the day, you just want, after you get this matrix, like let's say you have a complete matrix. So if you have
yeah.
this complete matrix, what you want to do is basically like just average across columns, because
Okay, got it. Yeah,
this would give us like the performance of the LLM for different prompt templates, basically, right?
yeah. Well, it would give
So
us the mean. It would give us like the mean performance, wouldn't it? It'd give us like the, if you average across them, it would give you like the expected performance overall as like the kind of the mean, I suppose.
yeah, so by
You
performance,
wouldn't capture the full distribution,
yeah,
I guess, if you like did a reduction.
yeah. So we have this matrix. We average across columns. So this would give us like the average performance across questions, right?
Yeah,
But then if we just average across
yeah,
columns, we have a distribution of scores because we still have the rows, right?
yeah.
So we are interested in estimating the distribution of the rows, basically. So after you average cross questions, you
Yeah,
still have like many numbers which are given by
yeah.
the rows. So we basically are trying to estimate the distribution of those numbers,
Okay, got it. Yeah,
which is given by this estimate in the bottom of this slide.
yeah. Okay,
Yeah.
okay, makes sense. Yeah, but thanks
Yeah,
a lot.
and then like after we get distribution, you can basically get anything, right? So
Yeah,
you can basically like get how a measure of sensitivity of your LLM. So basically, after you get all of these numbers, you can just maybe compute a standard deviation using these numbers.
yeah.
This is gonna give you like how sensitive your LLM is to different variations. You can also
Yeah,
compute like maybe some summary statistics as like the average performance of this LLM, or like median or
yeah,
top quantile or maximum or minimum, anything. So
yeah. Makes sense.
yeah, maybe I can show you guys a demo we have. So I think things can be more clear. So we have this GitHub repo, and this we have the implementation of our method here. Also, like everything you need to reproduce our results. Um, this is the demo we have. I can show like we can see how things look like in practice. So this demo, I'm gonna use MMIU data because that's one of the this is the data we produce ourselves. So this is basically the data we introduce in this paper. So for the ones that are not like familiar with MMIU is like a very big benchmark with more than 14,000 questions. But these questions are like separated by subjects. So for example, we have biology questions, math questions, physics, economics, computer science, and etc. So we have in total 57 subjects. So here we're gonna use MMIU, and the task we're gonna be focusing on is just high school biology. But this is just a choice I made because in this specific task, we have many questions. So I think we have like around 300 questions. So this is a good number. And in total, we have 100 prompt variations. So in total, you can see that we have around 30,000 questions, right? Possible evaluations. And this is a high number. So we want to make evaluation with much less than that. So using this data, let's load here and let's plot the performance of different LLMs for this specific subject of MMOU. Here we have 15 LLMs. And you can see that some of them, they have like a very big variability. For example, LLM 11, you can see here in the left side that its variability, like the difference of the top performance prompt template and the least performance performance prompt template is like around 20% points, which is very, very high. So we're going to focus on this specific model because it's a more challenging scenario for us, right? So basically, we want to estimate this distribution here that we see here in the left side for this LLM 11. So let's say we load the data for this LLM 11, and we're gonna use a budget of 1,000 evaluations. So out of like 30,000, we use just 1,000. So it's like less than, I think it's around 3% of total evaluations. So we basically have a matrix here that's going to tell us which one of these entries we're going to observe. And we sample this using stratified random sample in a certain way that the number of observed examples across a prompt pen templates is roughly the same. And also the number of prompt templates that respond to each one of the questions is roughly the same across questions. So here we're just sampling. It takes some time. So you can see that this returns us like this bidimensional array. And like this is just a Boolean array of falses and truths. And this is going to be false if we don't observe that specific entry, and true otherwise if we observe. So we're going to basically create an object called YSyn. And this YSyn is basically going to be minus 99. Just like this is just a placeholder for no observed entry. And where we will observe, which is basically here, this is an example, it's just 0 or 1, if that specific prompt template got that specific question correct or not. So we can see that the LLM got this question wrong, and here this prompt template got this question correct. And then we fit our model, which is the thing I showed you in the slides. Here we just use like a logistic regression. And as the features xi and zi, we just use one-hot encodings. So basically, for each one of the prompt templates and each one of the questions is going to be represented by a unique scalar. So I think this is the simplest version of the model, just using like one-hot encodings. And here we have some results. So basically, the blue curve here is just the distribution of performances for this specific LLM across different prompt templates. We also have our method, which is given by the orange curve here, using just one-hot encoding features. And here we have like a loss of 5%. I can explain better what this 5% means later. And here we have a baseline. The baseline is basically like we have this matrix of observed entries, right? So there are some scattered observed evaluations. And then to get the baseline, we just average across columns just in those observed entries. So I think this would be the natural like baseline, because it's just you sample some entries and you just average everything. So you can see that in this case, we do a bit better than the baseline. It's like we are closer to the ground truth CDF. but it's not like much better. It's just a bit better. So what we can do like to get better results. So what we can do is basically using more informative covariates. Instead of just using like one hot encodings, we can basically use better covariates for the prompt templates, for example. And that's what we do here. Here we have a box plot for the performances. And I'm gonna show you how this is gonna work. So basically we have different prompt templates, which are like these prompt variations. And here I'm showing you some examples. So like these are the first different prompt templates that we have. So for example, here we have like some text, and then we have like some fields that we're gonna put the topic of like this specific question, the question itself, and then like some space for possible choices, and then the LLM is gonna give us the answer. So it's more like a different format in the sense that one of the examples I showed in the slides. So we're not like using paraphrasing or like changing the text on the top of my question, but just giving like different formats of the prompt. So we have like for these different prompts, we just have like a different string, as you can see here. For example, this is one of the strings. This is the string for the second prompt templates, and etc. So what we're gonna do, we're gonna just use the sentence transformer library that give us like a pre-trained language model. We're gonna use this language model to encode my string using like a vector of features. So we use this specific model that is like a fine-tuned model that is pre-trained on different questions. So I think this is specialized to this specific task. And then for each one of the strings, we're gonna get a vector of like size 700, around 700, which is very large. And then we're gonna basically use PCA to reduce the dimensions here, because like the amount of evaluations that we make in practice is very, very small. So we also want to avoid work with many dimensions. So we use basically PCA to reduce the dimensions to 25 here. So let me run this. This takes some time, but I think overall it's fast. Okay, so now each one of the prompt templates is going to be represented by 25 numbers. But we still we found it in this paper that it's a bit harder to represent well like questions using embeddings. Like this doesn't work quite well. So for the questions themselves, we're gonna keep using the one-hot encodings. But for the prompt templates, we're gonna use these 25-dimensional embeddings.
Do you have any idea why that discrepancy is? I'd have thought that given they're both text-based, that using a text embedding would be better in both cases versus one hot. Do you have any idea why you see that difference?
Like we didn't observe an improvement, but like I think, yeah, I think for the questions, you probably need to have like a very specialized model for those questions to have like some meaningful embeddings. So, but we couldn't get these embeddings in the period that we were working on this paper. So that's why we didn't.
Probably to get the very best performance, you would want to have a model that is able to understand those and to also get a text embedding for the questions, I assume, or like could push things even further potentially.
Yes, I agree with you. I think in the best case scenario, we also would have like a good embedding for questions. I think that would be the ideal. And if you could do that, you could probably like instead of using 1,000 evaluations, you could use just maybe 100, and that would be enough.
Yeah. No,
so,
really
but that's something we couldn't find in this paper. But I think this is like a possible future direction. But I think it's important. Yeah.
That's good. Yeah, thanks.
Yeah, of course. So we're gonna refit our model using the covariates here, and these are our new results. So the only thing that changed here is that we have this, or we have the instantiation of our method using covariates now, and you can see that's much better than the other two possibilities. So we can get much closer to the ground truth using covariates for templates here. So yeah, and just a comment about these lots that I said that I would make a comment later. These lots is basically just a measure of distance between the curves and the ground truth. So for those familiar with optimal transport, this is just the Wasserstein distance between the blue distribution and the distributions that the other empirical distributions that are our estimates. So basically, we see that our method PromptEval with covariates is much closer to the blue curve when we compare with other possibilities. And finally, we just have a box plot here comparing the different methods we tried and the ground truth. And we can see that our method with covariates is much closer to the other when compared to the other two possibilities. Okay, so does anyone have another question about the things that I showed, or should
I
I
have
go?
a very quick question.
Yeah.
Just on the graph. So, do you see any trends in where the remaining uncertainty is? So maybe just scrolling up to the cumulative graph from before. So obviously, for the like low performing examples, we slightly overestimate the number of very poor performing examples, and then we slightly underestimate the number of like average scoring examples. So, we overestimate at about 0.3 on the x-axis, underestimate at about 0.6, 0.5 on the x-axis. Do you see any consistent trends there where there's certain regions where consistently things are overestimated or underestimated, or is it quite, I guess I don't know if you've done any evals on this, but what's the noise distribution on the error of like your method and the ground truth typically?
Yeah, I think that's a very good point. So I think we usually see this pattern here that you're seeing. So usually the methods, they usually overestimate the upper quantiles and underestimate the lower quantiles. And this is one thing. Other thing is that even if the method does not, different methods does not like estimate well upper or lower quantiles, like more extreme quantiles, like they usually estimate the median very well. So you can see that, for example, even the simplest version of our method, like which is given by the orange curve here, it gives a very good estimate for the median. So if you just want to get like the median performance, maybe you don't even need like 1,000 evaluations. Maybe you need like less. Maybe 400 is enough.
Yeah. Okay, makes sense.
Yeah.
Cool. Yeah, very, very interesting.
Yeah. And yeah. Does anyone have a question? I heard some sounds.
Yeah, Kato just raised his hand.
Yeah.
Do you have a question, Kato? Do you want to unmute, Kato?
Yes, I have a question.
Yeah.
So I wanted to ask, how does PromptEval use item response theory to improve the evaluation of LLMs across the different templates?
Oh, how we use item response theory?
Yes.
So let me go back to the slides.
Do you want to mute quickly, Kato, because we can hear the speaker? Yeah, perfect. Thank you.
So basically, this model here that we use, you can see it as a variation of the item response theory model. Actually, if you just like use instead of using embeddings or anything, if you just use like one-hot encodings for both the x's and the z's, and if you use like a linear model, the which would be like the logistic regression model, this is equivalent to one of the item response theory model, which is called the Rush model. So like if we go back to the demo, if you see here, for example, like when we instantiate our method, it's called extended Rush model because just an extended version of one of the IRT item response theory methods. So I think our method is related to item response theory because we get some inspiration in the models people use in this literature to create our own model.
Awesome.
Yeah. Did that respond?
It seems like it. We got a thumbs up. So yeah, awesome.
Okay.
Thanks a lot, Felipe.
Thank you.
So I guess maybe have you got a few more slides or?
Yeah, I got a few more.
Okay.
There. So basically, I wanted to talk about some results that we have. So in our experiments, we basically focus on 3 benchmarks. So one of them is the MMIU we talked about earlier. The second one is called Big Bench Hard. And the third one is elementary. And for each one of these benchmarks, we have basically data from 10 to 20 LLMs across like different prompt templates. So in general, like for these benchmarks, we have from 100 to 200 prompt variations. So as you can think of, like the number of possible evaluations is very, very high. So we want to make this evaluation more efficient. So in general, what we show is that 800 evaluations out of like 30,000 is enough like to get accurate estimation for like some key quantiles of interest, like for example, median or like quartiles or even top like 95 and the bottom 5% quantiles. In our experiments, we use embeddings for prompts. So basically, we use this Centron Transformers library to get some pre-trained embeddings, as I showed you in the demo. We also use a fine-tuned BERT model. And to fine-tune this BERT model, of course, we need to assume that we have some training set. So we assume that we have some training set for some LLMs, and we use this training set to basically fine-tune this BERT model to get more meaningful embeddings. But we know that in practice, it's very, very hard to get this training set because it's very, very expensive. So we see this like as an improvement of our method if you can get a training set, but this is not really needed in practice. And we also use some discrete features for prompt templates. And these discrete features are just like if some templates have commas or like have semicolons, or if the letters are capitalized or not, these kind of features that can help. And for example, like for questions, we just use one-hot encodings because in our paper, we couldn't get like more meaningful features for encoding questions. But we agree that if one can do that, that would be very helpful. And the main baseline that we consider is just the simple baseline of averaging seen questions, observed questions. And for all like methods and baselines, we consider sampling with stratification, so we can have like a more balanced sampling pattern. Okay, these are our results. So the baseline is given by the brown curve. For each one of the rows, we have different benchmarks. And for each one of the columns, we have different quantiles that we want to estimate. X-axis give us different budgets, like the number of evaluations we want to make. So you can see that for oral methods, we are doing like much better than the very naive baseline of just averaging across like observed evaluations. The blue one is just like the simple model of just using one-hot encodings. This does quite well, like compared to the baseline, but of course, if you use some nicer features, you can get better results. And we show that also, I think another very nice result is that the pre-trained embeddings work very well. they work well across different benchmarks. The fine-tuned embeddings work better, but they are expensive to obtain because you need to have the strain set. We know that. And the discrete features, they can work better or worse depending on the data set. So I think this is very data set dependent. And finally, we consider a last application, which is just one extra application of our method, which is just like let's say you have a pool of possible prompts, and each one of these prompts is going to give you, like, of course, a different performance in your task of interest. So we want to find the best prompt in this pool of prompts. So basically, you can see this problem as a bandit problem of best arm identification. So you just want to find the best prompt, like in this certain pool of prompts. So actually, there was a paper that introduced this idea of best prompt identification, which is like very, very recent. And the thing that we show is that using our model and their idea of using bandits to find this best prompt is a good combination. We can basically improve their results by using our model. But we still use their algorithm to find the best prompts. And we show that the regret using our model is lower than using the model they propose in their paper. By regret, I mean like the difference of the best performing prompt performance and the prompt that we think is the best one.
Quick question: Are these error bars like the standard deviation, or is it the min and max across the tests? Because there's quite a high variance.
Yeah. So this is basically the we repeat this experiment for different seeds, and these are like just the standard deviation across seeds.
Okay, so like for example, with those bottom three, then basically there's no distinguishing them because it looks like the standard deviation is quite a lot bigger than the points themselves. So, but it is split from the top three. The triple ones are quite distinct in their standard deviations, it looks like. So yeah,
so the bottom three are basically, we are using this method of best prompt identification, but we use our model, so we get this bottom three methods. And for the top three, we just like use the model they use in the paper that introduced this idea.
Yeah, makes sense.
Yeah. So this result is for MMLU. This is one example. So we can show that we can improve finding the best prompt if you want to using our model. Well, that's it. I think we have maybe some time for questions. So
yes, well, first of all, I just want to say, huge round of applause for Felipe. That was an incredible talk. Let's all give a big round of applause. Again, as usual, I certainly have a few questions, but maybe I'll open it up to the room to start with. So anybody in the room has any questions at all to start with? Otherwise, I can kick off. Okay, well, I guess my first question is, I don't know whether it's something you've explored or not, because I know you're doing a lot of open source models that are actually tractable to run these obviously very expensive experiments to run. But have you observed a trend where the bigger, higher performing models have decreasing variance in the prompts? Because I would assume that GPT-4 and Claude Opus and so on are much more robust to the reframing.
Yes.
Not totally. Obviously, it's like one of the big things of just like still prompt engineering and getting all done perfectly. But in terms of like getting answers right or wrong and being thrown by, we've seen examples where we've used like Gemma, and if you ask it for the largest number in a set, it will try to turn the numbers into strings and like look at the longest string or something. And if you say the biggest number, then it will do it correctly or whatever. But like obviously GPT-4 is a lot better. So yeah, is that a trend you've seen?
So yeah, in this paper we didn't explore like we just explored open source models, like open models. But there's this other paper that we basically cite, and this is one of the papers I showed in the beginning of that they explore this sensitivity across prompts, and they conduct
Yeah.
a study with like proprietary models, like bigger models, and
Yeah.
they show that the durability is like smaller, but there's still some variability. Yes, but even in that paper, like because it's very expensive to do this kind of like study with like closed models, so they even like do sampling. So the study is not also very comparable to the other.
Yeah.
But we didn't use because it's very expensive.
Yeah. No, of course. And I guess like how do you think this compares? So I guess at the moment the only what you were testing was obviously these reframings of the same question. So whether things are capitalized or not capitalized, or what order things are put in, and so on, and these kind of standard templates. Did you include things such as chain of thought, like think step by step, or anything like this, or was it more like, I guess what were like, it'd be interesting to just get a bit of a sense about what the variations were exactly that was your like templates for variation. What did that typically, you showed a few examples at the beginning, those are nice 6 examples early on. You showed a few others at some point in the notebook. Actually, I think you showed a few examples, but maybe just like describing like what kind of thing are we doing in these reframings typically?
So I think that we did different things. So basically, in our evaluation, we use 3 benchmarks. So one of them is MMLU, and for that one we like collected data ourselves. And for that specific benchmark, we use these different formats. So like we added space, columns, comma, etc. Like, but for the other 2 benchmarks, they are collected from. They were collected by other people, so they were introduced in a different paper. And in that paper, they also have like some paraphrasing. They have like they use chain of thoughts and etc. And then they have some sophisticated ways of doing that.
Got it. Okay, and it's a data set that they extracted that already has like a large collection of rephrasings of the question, and you kind of use that data basically, right?
Yes.
Maybe they also used an LLM to like reframe things or something. I guess that's something you could do. Interestingly, actually, as well.
Yeah. People do that.
Yeah. Okay, makes sense. So a couple more questions come through on the chat. So Kato has an additional question, which is, what challenges did you encounter when applying PromptEval to different benchmarks like MMLU and Big Bench Hard, and how did you address these challenges?
I think the biggest challenge is because like these benchmarks, they have like different, like they have of course different questions. So how do you like encode different questions? So this is one thing that is challenging. And another thing is how to encode different prompt variations, because like if you have paraphrasing, it doesn't really make sense to use like discrete features that finds like presence of commas and etc. But it makes more sense to use embeddings. And like if you use different formats, like adding comma, subtracting comma, etc., it makes more sense to use like these discrete representations that count the number of like symbols and etc. So I think that the biggest challenge here is how can you like find good ways of encoding first prompt variations and different questions. I think this is the more challenging. And
makes sense.
We could like overcome the prompt variations using embeddings, also like discrete features, like these discrete features, but we couldn't find like a really good way of encoding questions. So that's an open-ended.
Yeah, no, it's definitely an area for some maybe future work. And then SS Manjanath asks, was there any difference in behavior from model and its quantized version?
Oh,
I guess that wasn't tested.
Yeah, we didn't test any quantization, but I guess there should be some difference, maybe. Yeah, but
I guess you can imagine that maybe the variation of a quantized version, if anything, will increase. I would assume. But yeah. Maybe it depends. The performance will definitely decrease in general. I guess whether that corresponds to an increase in variation is not clear, but I guess it probably would. Okay. Well, I think I could ask many questions, but I think we'll try and stick to the time. But it was really amazing having you with us, Felipe. Let's give another
Thank you
big
very
round of
much,
applause
Daniel.
for an amazing talk.
you.
Obviously, I'm sure you're going to keep churning out many great papers. So, when the next one drops, then we'd love to have you join us again and present all of your latest great work. But yeah, for now, it was really great having you join us, and looking forward to seeing you again at some point. And I'll see everybody again same time next week for our next paper. I'm not sure exactly what it is, but yeah, we'll be having another great paper as usual. So see you guys all again same time next week. And again, thank you very much, Felipe, for joining.
Yeah, thank you very much for the invitation. It was very good to be here with you. Thanks, Daniel.
Of course. Thanks a lot, everybody. Have a great week. Bye-bye.
Bye.